The E2 reaction is a bimolecular elimination that occurs in one concerted step. Bimolecular refers to the fact that the rate-determining step of the reaction depends on both the concentration of the substrate as well as the base. A strong base is generally required in order to displace the leaving group and form an alkene as the final product. Primary alcohols tend to undergo E2 elimination reactions. This is because E2 eliminations occur in one concerted step and avoid the formation of carbocations altogether. The dehydration reaction of alcohols to generate an alkene proceeds by heating the alcohols in the presence of a strong acid. The OH group of the alcohol is not a very good leaving group by itself, but in the presence of a strong acid, the OH will act as a base and deprotonate the strong acid, thus forming an OH2 plus group instead. This is a much better leaving group. The water present in the solution will act as a base and deprotonate the beta hydrogen of the alcohol, and then in one step, the protonated alcohol group will also leave. This will form the desired product. We stated that E2 requires a strong base in order to work. In this reaction, it occurs at high temperatures. At high temperatures, any base will work. Since water is the only base present in the reaction mixture, water is the base that will be used in this mechanism.
Zaitsev's rule states that an E2 reaction will preferentially form the more stable alkene, or the more substituted alkene. This doesn't factor in when eliminating from a primary alcohol, as there is only one beta carbon from which to take beta hydrogens, which means that there is only one product that can be formed anyway. However, it comes into play if alternate methods are used to turn the secondary or tertiary alcohol into a better leaving group. When this is accomplished using a sulfonate, the leaving group behaves similarly to an alkyl halide, meaning that secondary and tertiary of these new leaving groups can be eliminated with E2. Here is another method of creating a better leaving group, other than protonating the OH group. Once the alcohol has been converted into a better leaving group as a tosylate, we can use a strong base such as methoxide with a negative formal charge to act as a strong base and deprotonate from the beta carbon that will help us form the more substituted Zaitsev product. And if we follow the electron pushing arrows, the electrons from the carbon to hydrogen bond here will help to form a double bond between these two carbons. And to avoid overfilling our octet on this carbon over here, these electrons will leave with the tosylate group, leaving us with the more substituted and more stable Zaitsev product. The product will not be this. This is only a di-substituted alkene. Well, here we have a tri-substituted alkene product. This is the Hoffman product, which does not usually occur under these scenarios. The elimination of the hydrogen and the alcohol group needs to be done in an anti-paraplanar fashion. Now, what does anti-paraplanar mean? It means that if you have a flat plane here, and the stereochemistry of the molecule has the alcohol group pointing one way, then the stereochemistry of the desired hydrogen to be removed from the beta carbon needs to be pointed 180 degrees in the other direction. Now usually, with the elimination of a primary alcohol, you never really have to worry about this because the primary alcohol, the carbon that the alcohol is attached to, right here, is only attached to one other carbon. We had a secondary alcohol here that has been converted into a tosyl group already to make it a better leaving group so that it can undergo E2 elimination. Now, one would expect to form a Zaitsev product, which would mean that a double bond would form here and the tosylate group would leave. However, this is not the case. This does not form. Instead, we form this product, which is the less substituted Hoffman product. And the reason for this, if we come back and look at the reactant, is that the stereochemistry of this molecule has a tosylate group pointing away from the plane of the board. However, the stereochemistry of the molecule has this methyl group pointing in an anti-paraplanar fashion away from that group. Now what this means is that this methyl group is occupying the space that the anti-paraplanar hydrogen would need to be removed in an E2 fashion along with this tosyl group. And so, E2 elimination cannot occur between these two carbons. Instead, the only carbon that can have paraplanar hydrogens would be this carbon here. And that's why once we use a strong base, we end up with this product.
And this concludes our explanation of the E2 dehydration of alcohols and the general mechanism that forms an alkene product from a primary alcohol. Don't forget your Zaitsev's rule, which forms the most stable alkene with the most branching. And your beta hydrogen must be anti-paraplanar to the alcohol group.